Hello, my name is Brady Kuzma. I'm here to present our work on producing efficient matrix multiplications using IBM Power 10's matrix multiply assist in the LLVM compiler. First of all, what is matrix multiply assist? It is an evolution of the vector scalar extension, which was previously available in Power 9 and still in Power 10. It is Power 10's matrix multiplication facility, meaning it is specifically focused on producing matrix multiplication operations. It supports a wide range of types that help both AI and HPC applications. These are things like 4-bit integers, 8-bit integers, 60-bit integers, as well as floating bit types such as the 16-bit floating bit type and Google's Brain floating point 16-bit type, as well as floats and doubles. Importantly, it is an outer product and not an inner product facility, meaning it can model some operations that other architectures can't very easily. How do we benefit from this? Well, the first thing is to leverage investment in specialized libraries, such as IBM's ESSL, Eigen, and BLAS interfaces such as OpenBLAS. How do we put these into code? Well, we first need to Americanize a pattern such as matrix multiplication in LLVMIR. We do this by first breaking down a matrix multiplication into its parts. There is a reduction operation and a loop nest. This loop nest is at least 3 deep, but it could be more if there is packing operations involved. When we put this into IR, we can see we look for a pattern starting with the reduction operation, which is this multiply and add combination. And from there, we can build up a pattern that finds loads and the loops, and we are able to determine access orders for the matrix multiplications. Of course, we also have data flow analysis to verify that code that we will be replacing is safe to replace and there are no other side effects. All of this work is available in an upcoming paper in Taco. So some results from this work, replacing these native code gems with library calls on Power 9. We can see that we significantly speed up some benchmarks using BLAS or platform-specific libraries such as MKL, Bliss, or ESSL. The current solution in LLVM called Poly is a polyhedral optimizer that has a specific module focused on matrix multiplication, doesn't quite compete with the other libraries. That being said, invoking a library is not always performant. We can see that for very small matrices and for quite a while, LLVM's O3 code either beats libraries or is very close to it. It's not until large matrices that we start seeing a significant difference from the libraries. So therefore, we look towards a compiler-only code generation path. And we do this through taking a layered approach for data movement in the memory hierarchy. We start by looking at the work of Goto and Gain, who produced a paper that was focused on high performance matrix multiplication, and we adapt it to our work in LLVM. So we start by taking the matrices A and B and tiling them to fit in cache. The MC, KC, and NC dimensions are these specifically chosen to fit in cache. We then take these tiles and break them down further into tiles that fit into registers. Each of these registers, or each of these tiles is packed in a special buffer to aid memory accesses. Once we have this, we can then move on to thinking about how we lower the operation. So we will start from a front end like Clang, which produces IR, and we get to an optimizer. In this optimizer, we will recognize a naive matrix multiplication and replace that with a packing operation and a call to the LLVM matrix multiply intrinsic. This intrinsic is meant to be used for small microkernels and can be efficiently optimized within the compiler for small operations. Once we have done this replacement, a later pass will take this intrinsic and replace it further with vector operations. These are basic vector operations that any backend currently supports. However, we would like to make use of Power. So while this works, and we will show results later for all platforms, we want to produce an extra version that works better using matrix multiply assist. So what we can do is, instead of replacing with LLVM vector operations, we can change to using PowerPC specific intrinsics that will be lowered by the backend to produce the assembly code at the bottom. Some results from this work. Using only the vectorization versions, we attain about half the performance of libraries for large matrices. Seeing here, we have two methods from ours. We have tiling and with no packing, as well as tiling and packing. We see that tiling and packing can attain results very near the optimized libraries for large matrices. And note that we can consider this approaching performance because this is already many, many times speed up over the naive code. We are better than the libraries for small matrices. We now include the intrinsic method, which could not previously handle such a large matrix without tiling. So we can see here that tiling is once again approaching the performance of libraries, but the overhead from packing makes the tiling and packing version slower than only tiling. Nevertheless, we still are beating or approaching the performance of optimized libraries. If we are to add in MMA, we can find out that we are twice as fast as the vectorized code and faster than libraries for large matrices. So once again, we're looking at large matrices with tiling and packing only using vectors and tiling and packing using MMA. The MMA is significantly faster and is beating the performance of Eigen while approaching the performance of BLAS. Note that these results here using MMA are not finalized, and therefore the performance is normalized to the BLAS runtime. These results are expected to be proportional, but are not the true numbers aren't representative of the actual system. I want to thank IBM for their help in producing this work, especially Kit Barton and Jose Moreira.